We're gonna resume the talks in a moment with the first talk from the main organizer of this workshop. It's my pleasure to introduce Majid Khadiv. He's a postdoc scholar in Movement Generation and Control Group at Max Planck Institute for Intelligent Systems, where he mostly focuses on theoretical and empirical aspect of locomotion for a legacy system using optimization techniques. Before joining Max Planck, he was a visiting student at Movement Autonomous Motion Department, and he received his bachelor degree from Isfahan University and his master and PhD from KN2C universities. And he was also since 2012 to 15 was an acting head of the Dynamics and Control Group in Iranian National Humanoid Robot Project, Serena 3. Majid, we're waiting to hear your talk. Stage is yours.
Okay, thanks a lot, Farbot. Do you hear me?
Yes.
Okay, great. Thanks a lot for the introduction, and thanks a lot for joining. My name is Majid. I'm, as Farbot said, I'm a postdoctoral researcher in the Movement Generation and Control Group in a close collaboration with Machines in Motion in New York University. Today, I'm going to be talking about one open source hardware project and two open source software projects I've been working on during the past 3 years. So a bit of motivation. I'm always fascinated and impressed by the dynamic and agile motions that human and animals can do. And I believe that if we can do similar behaviors or the same behavior using our robots, we can say we are at the stage to have humanoids or animaloids counterparts of the human and animals. This is the state of the art in the robotics field, locomotion robotics field. These are all from companies. These robots are from companies. We have on the top, you can see two quadruped robots, which are Spot from Boston Dynamics. On the right, you can see Unitary robots. They are very now mature technology. They can do agile motions. However, the hardware and software for these robots are closed source. So for the researchers, we cannot see what they do exactly. We cannot modify the software and hardware for our use case. Also in the bottom, you can see Boston Dynamics Atlas and Agility Robotic Pesci. These are state-of-the-art robots in the humanoid or bipedal locomotion field. But again, all the hardware and software for these robots are closed source. So today I'm going to talk about first a hardware initiative, an open source hardware initiative, and then about two open source softwares. First one is about fast replanning of the step location and timing, and the second one is a general purpose planning software. Okay, Tuma has talked a bit about Open Dynamics Robot Initiative today. So this is an initiative which has started about 3 to 4 years ago through a collaboration between Max Planck Institute, New York University, and LAS CNRS. So from Max Planck, Felix Germinger is the main contributor. He is the mastermind behind the mechanical design and mechatronics in general. And from the LAS side, we have Toma, who is designing and improving the kinematic the electronics of the robot. So this is the GitHub page of this robot. Thanks to the effort, especially from Felix Germinger, it's very well documented. So you can go ahead, check it out, and you can see all the components you would require in order to build your own robot, own legged robot or manipulator. Here is a more detailed design and also all the robots we have developed through this initiative. On the top, you can see first on the left, you can see the actuator module, which is a combination of a brushless DC motor and a two-stage timing belt pulley. Then you can see the 3D printed parts that you need for the shelves, for the actuator shells. Then there's a body structure that are also 3D printed. And finally, we have the custom electronics. These are the main parts of the robot. On the bottom, you can see the robots we have developed. On the left is Solo 8, which is the first version we developed. It's a super lightweight. The weight of the robot is less than 2 kilo. That's why it can perform highly agile motions. Solo 12 is a kind of improved version of Solo 8 in terms of maneuverability, I would say, because it's able to traverse all the surfaces in different directions, and it's not limited the motion that it can do. Also, you can see Bolt, a biped version of this robot, and also Three Finger, which is another version that you can have in-hand manipulation. So these are the set of robots that we developed in Open Dynamic Robot Initiative. All the parts and the procedure to build these robots are well documented. You can go to the Open Dynamic Robot Initiative GitHub page and see how you can build your own robot. So here is a one actuator module. It's comprised of a brushless DC motor, and then we have 3D printed pulleys, and we have encoders, shaft, and the timing belts. All the components are either off the shelf available or 3D printed. So the whole weight of the core components is 96 grams, which is super lightweight. And then on top of these modules, you can build the robot. This is the first robot we developed, this Solo 8. On the left, you can see this robot has some very unique features. It can just rotate its knee and have different configurations. It can step on top of obstacles by rotating more than 180 degrees up to 360 degrees of the hip joint. Also on the bottom, you can see that thanks to the symmetric design of the robot can just flip its leg and stand up from a fall. Also on the right, you can see some features of the Solo 12 robot. You can see the range of motion from abduction adduction joint is very huge, which means that the robot is able to do very special movements. Here is some features through videos. This robot is fully back drivable, fully torque controlled, thanks to the transparent design of the joint modules, which means that all the forces at the output of the joint can be seen by the motor. The robot can rotate its knee. I will show in the next slides how we can use this feature to perform some unique motions with this robot. Again, as I showed in the previous slide, the robot can just simply rotate its legs and stand up from a fall. And finally, and most importantly to me, is that the robot is impact friendly, which means that we can, in theory, generate very dynamic motions with on this robot without having this fear that we would break the robot or we would damage the robot. So this is the nicest feature of the robot. Also, at the same time, the robot is not so expensive. Even if we break the robot, which is the case sometimes, it's fine, and we can just simply repair the robot. Okay. So this was all about the hardware. Now I'm gonna go to fast replanning software that we developed, which is based on step location and timing adjustment. So I'll give a bit of detail about the structure of the dynamics, which I think it's essential for understanding what's going on there. So if we simply look at the equations of motion for a legged robot or a manipulator or any robot that makes and breaks contact with the environment, you have a continuous time dynamics like this, which is an ODE with some constraints. As long as the robot doesn't hit the switching surface, which is shown here by H. But as soon as the robot hit the switching surface, the robot state goes to a reset map. And this is the reason that we have a hybrid system. And it's really hard to control hybrid systems in general. If we look at the continuous part of the dynamics, we have actuated part and unactuated part. The actuated part is simply like a manipulator dynamics, which says that we need to exert torque such that we are able to exert force to the environment. However, the interesting part of the dynamics is unactuated, which says we need to exert force to the environment in order to control the center of mass motion of the humanoid or legged robot. And essentially, this dynamics is unstable, which means that we need to properly control the force, which is highly constrained, to be able to stabilize the center of mass motion. So these dynamics can be captured using centroidal momentum dynamics, which says that the sum of external forces is equal, which is the Newton-Euler equations of the whole system. And it says the sum of external forces is equal to mass times acceleration. This dynamic, the centroidal momentum dynamics, is in general nonlinear, and it's really hard to design controllers for this robot. That's why normally for walking motion, we resort to using LIPM, which is an abstraction or a linearized version of this dynamics. And it says that if we consider that the center of mass height is fixed and the rate of angular momentum around the center of mass is negligible, we can write down the equation as a linear dynamical system. And finally, this is a kind of block diagram we normally use for controlling these robots. We are given a desired behavior. For instance, for walking, it's a desired velocity command from a joystick, for instance. Then we plan trajectories for the most important parts of the system, which are normally center of mass and end effectors. And then we pass these trajectories to a whole body controller, for instance, inverse dynamics, and we produce torque for the robot. The whole body controller is always based on the feedback from the system. However, the trajectory optimization problem can be either through feedback, which is called, and we have replanning based on feedback, which is called MPC, or it can be only offline, or it can be done only once for the whole motion, which is called normal trajectory optimization without using feedback. So this is the whole structure of the dynamics and control of the gate system. So one of the questions that I believe is very important is that given the very different structure and morphologies that humanoid robots have, could we have a walking controller that can stabilize them independent of the type of actuators they have? For instance, in this picture, you can see that Hermes in the right picture is a fully actuated system with many degrees of freedom. For instance, each leg has 7 degrees of freedom, and it has arms, upper body, and so on. So the robot has full control authority over all joints and on the interaction force. However, the weight of the robot is super high, which means that the robot is not able to do agile motions. In the left, you can see Bolt, which we designed through Audrey. It's a minimal biped robot. So it has 3 degrees of freedom per leg. So it's very minimal in terms of controlling the interaction with the environment. However, because it's very lightweight, it can do very agile motions. And also in the middle, we can see, for instance, another type of design, which is based on passive ankles and kind of fixed angle and prosthetic fit. So the question I would like to answer here is that, is there a walking controller that controls all of these robots? So here, since we want to only tackle the walking motion, LIPM or linear version of the dynamics, centroidal dynamics is enough. And the whole point that we make here is that in order to control properly the motion, we only need to adapt the switching surface, which means that if we are able to adapt the step location and timing, we are able to build a very robust controller for legged locomotion in general. So here is the idea at each control cycle. So here you can see that trajectory optimization part also uses feedback from the robot. So we do a very fast loop on the robot at each control cycle, which is 1 kilohertz, to find that the optimal set of next step location and timing. Then we have a block that generates swing foot trajectory given the current state of the swing foot and endpoint. And finally, we pass this trajectory to the inverse dynamics to track these trajectories. This is the whole pipeline. So if I want to go a bit more through the equations, so here is a very simple QP that we constructed for doing step location timing adjustment. So U is the next step location, tau is a transformation of the step time, and B, which is very crucial in our algorithm, is we call it DCM offset. It says if DCM is divergent component of motion, which is a combination of the center of mass and center of mass velocity state. So if we say that if we are able to limit the distance between next step and the DCM, which is the divergent part of the center of mass of motion, we are able to capture the system in a finite time, and we are able to guarantee a quality which is called viability of the system. So here is the dynamics. C is center of mass, psi is DCM, And you can see that the Xi is unstable dynamics while center of mass converges to the Xi or the DCM. So we can put all the constraints, kinematic constraints that we have. For instance, the next step location is limited with respect to the current one. The exponential of time is limited also. Step time is between T min and T max. This exponential of time is essential in order to have a linear dynamics. Here we can see in 2D that the equation is linear with respect to tau. And finally, we have 2F, which is we call it a viability constraint, which which is a terminal constraint for this problem and constrain the distance between the DCM and next step location. And this can guarantee for us the viability of the gate. So this is the first level. So what we do is that given the current state of the system at each time control time, we plan the next step location and timing. And then we generate here, I generated a simple polynomial based trajectory for the swing foot to track this trajectory. This works well in simulation. So you can see here the robot is pushed and it's able to recover from these pushes using step location and timing adjustment. Also here is a slippage recovery, for instance. So here we show that also timing adaptation is very crucial for robustness of bipedal locomotion. In general, we have shown that there is no need actually to explicitly control center of pressure and center of mass for walking. The only thing that we need to do is that we need to adapt the step location and time. Also, we showed that we can guarantee viability of the gate using only one switching surface in the horizon. And finally, we can do very fast replanning thanks to the formulation of the problem through a very small cube. Then, in order to have a better swing foot trajectory generation than a polynomial, which is a naive way of doing that, what we did with Elham, who is actually an intern in our lab, is that we tried to map the full dynamics of the system, which you see on top, to the swing foot. I will not go through the detail of the equation. I'll just give a very high level representation. So if we map the dynamics, full dynamics of the system to the swing foot, considering that the stance foot is limited and is constrained, we end up having this dynamics, which is comprised of an inertia term and some nonlinear terms. Here, P is a null space projection that projects the null space projection of the contact and constraint. So here, what we did is that we just generated a different number of walking gates, and we have seen that, and we have plotted the nonlinear terms in this equation and inertia term. And we have noticed that the most important or prevailing effect is the inertia term and not the nonlinear term. And the other interesting thing is that the nonlinear term is pretty much fixed at the swing foot. And then for the inertia term, what we did is that we only tried to plot the components of the mass matrix projected at the swing foot. And also we saw that we can also very well estimate that with a linear, each component with a linear term. And finally, we can end up having this linear dynamics, which says the amount of force at the end effector, which means the amount of force available at the end effector given the contact constraint and the torque constraints in the joint, is equal to the mass matrix, which is interestingly, it's not diagonal, times the acceleration of the swing foot plus some nonlinear terms. And by considering that the mass matrix and the nonlinear terms are constant, we end up again having a quadratic program for generating the swing foot. So we tried this on a real robot, Bolt. Here with the polynomial-based trajectory generation on the robot, we were not able to realize the walking controller on the system. However, based on this optimal control-based MPC of the swing foot trajectory generation, we were able to realize this motion on the robot. So here is a velocity commanded motion back and forth on the robot, and the robot is able to track this motion. We also did some tests on uneven surfaces. Here again, the robot is adapting step location and timing, and thanks to the torque control strategy, the robot is very compliant, so it's able to tolerate some kind of unevenness in the environment. Okay, the next test is working on soft surfaces. Here again, in the control design process, we assumed that the contact is rigid to have a simple equation. However, we tested the robot on a soft surface and we saw that the controller is robust to this kind of uncertainty. We also performed some disturbance rejection tests. The robot is pushed away in different directions here. And again, it's adapting a step location and timing to recover from these external disturbances. Here is some push recovery in sagittal plane. I hope you can see the videos in a decent quality. If not, you can go ahead and search the paper on YouTube and see the videos. And finally, we also test the robot on some moving platform to see if it's robust against some kind of slippage recovery. And we noticed that it's indeed robust to some level of motion of the stance foot. Okay, the same control framework has been used by Julian, a PhD student in New York University, on a quadruped robot. And again, here the robot is able to walk robustly on different surfaces. Here, these are all disturbances. They are not planned. They are not considered in the planning stage. However, the controller is robust enough such that the robot doesn't get unstable in the presence of these uncertainties, basically. And the robot is joystick controlled. And thanks to the step location and timing adjustment, it's able to do some kind of disturbance recovery. So all these videos are again available on the Audrey YouTube page. You can go ahead and watch all these videos with a better quality. Here is Julian is pushing the robot, and thanks to the very reactive step location and timing adjustment, the robot is recovering from these disturbances. Okay, so thanks to the work of especially Elham, now we have this software open source. You can go ahead in Machines in Motion GitHub page. Reactive planners, both the polynomial based and optimal control based approaches are available there. You can go there, use it, and if you have any problem, you can open an issue and ask questions. Okay, now let's move on and see how we can generate more complex motions, how we can, for instance, have multi-contact interactions with the environment, how we can do very dynamic motions like a backflip and so on. Here I'm introducing another software, which is a more general purpose approach. You can do full body, you can generate full body trajectories for multi-legged robot through a unified framework. So here we cannot use any more LIPM because we want to move the center of mass in vertical direction, and also we would like to have angular momentum for some dynamic motions. So that's why we resort to using centroidal momentum dynamics, which is nonlinear and non-convex, and it makes the optimization problem non-convex, which means that we cannot, first of all, solve it very fast, like 1 kilohertz. And at the same time, we cannot actually give guarantees in terms of constraint satisfaction and so on. Also, what we need to do is that we cannot only consider the switching surface, but we need to design plans for the center of mass motion and the contact forces to make this kind of motions possible. Okay, this software that I'm gonna present, which has been also published in a EEE Transactional Robotics, is based on the work of Brian in his PhD. So the idea is that we can have two optimization problems for this system. First, we can have a centroidal momentum dynamics, which is, as I said, the dynamics, the constraints are non-convex. So this optimization problem is non-convex. However, there is a very known structure in this dynamics, and we can use it to have a very fast centroidal dynamics based solver. So we can solve this problem kind of quickly. And then what we can do is that we can solve a whole body kinematics such that we consider all the whole body constraints and try to track the centroidal trajectory. So rather than solving the whole body trajectory optimization as one block, what we do is that we just separate them, and then what we do is that we solve each problem and iterate between these two solvers until they come to a consensus. This is very similar to a kind of block coordinates descent optimization problem that we have. We write down two optimization problems, we solve them, and then by increasing the weights of the consensus objective, we can push the solutions toward the region that we are interested in. So with this optimization algorithm, for instance, I started generating some motions, some non-trivial motions on a quadruped robot. Here is this robot Solo 8. This motion consists of some non-trivial sequences. We have first some kind of multi-contact motions where the robot put its foot on top of this block. And then what it does is that it jumps on top of this box. And then it rotates back its the hip degrees of freedom to come to a natural position. So this motion is kind of very tricky to generate. However, thanks to the very fast solver that we have, we could generate this motion on the robot and execute it on the real system. Here is another motion which well shows the dynamic capability of this Solo 8 robot. The robot standing height is 21 centimeter. However, the robot is able to jump around more than a meter, I think. And this means that it can jump more than 5 times its standing height. And this is thanks to the very lightweight design of this robot. So here, what's tricky is that the robot, we need to change the gains if we do trajectory optimization on the system. So changing the gains is crucial for this kind of motions to realize. We need to have very high joint gains or impedances in order to generate so much thrust that the robot can jump so high. And then for the landing part, we need to decrease the gains and increase gain, I mean stiffness, and increase the damping such that we have a very nice and damped landing. And here it's only based on heuristics. I just interpolated between the gains such that we have this nice behavior, but in general, we can have more systematic ways to do it that you can see in our papers, for instance. Okay, this software is also open source in Machines in Motion group. It's called Kinodynamic Opt. And you can go ahead and try it. And if you have any problem, you can open an issue and ask your questions. Okay, so I think I'm pretty much done with my presentation. So first of all, to just summarize, I presented ODRI, where the main goal is to enable access to a very low cost and high performance locomotion and platform. I'm not saying that this platform is actually the best platform, but I think for the research use cases, I think it's very well suited. So you can modify the design if you want. You can just buy everything that you need for building the robot. And because you are assembling it yourself, you may be able to just debug things and so on in terms of hardware. Also, I showed that by focusing only on the switching surface adaptation, which is step location and timing, we can have a very robust controller for legal locomotion in general. And the reactive planner software that I showed is based on this idea. And finally, I showed that exploiting the underlying structure of the equations of motion of a legged robot, we can come up with a very efficient solver that can generate very non-trivial motions, multi-contact and dynamic motions on the robot. With this, I would like to also thank my collaborators in all of these projects, and also my friends in Machines in Motion in general. Thanks a lot for watching my talk. If you have any question, please feel free to ask.
Thanks a lot, Majid. Very nice presentation. Okay, so we can now start with the question rounds. If you have a question, either raise your hand or post it on the chat. Maybe I can start with the first question. So in the last work that you present, this centroidal model trajectory optimization, what are the assumptions what is the input you need to this trajectory optimization? Do you need the timings and mode switches, or that is something you also optimize over?
Yeah, so here it's possible that you optimize over timing, and also, so it's not, so in order to do mode switches through an optimization problem, we can have another layer through mixed integer. But the thing that I showed here based on kinodynamic itself, it's not able to adapt the mode switch, but it can adapt step location and timings, yes. Step location is trivial to add to do this formulation, and it remains the same. It's a convex part. The timing makes it non-convex. However, again, if we use Euler integration algorithm, and also we consider that, for instance, the control zero Euler Hort, or the control is fixed during time, we can end up having the same bilinear constraint in our problem, and then we can use the same trick that we use for centroidal, which is also biconvex, and solve this problem.
Adding a third layer then.
It's not a third layer. You can solve it with the same optimization problem, but it's more time consuming. So if you add the discretization time as a new variable, what will happen is that you will have the control input times discretization time as a bilinear kind of constraint, but it's the same in nature constraint compared to, for instance, centroidal momentum, where you have, for instance, force times center of mass or acceleration times center of mass. So both of them are bilinear constraints. So if you use this structure, if you write down a solver that can handle bilinear constraints through with an efficient way, then these two problems are the same. So this problem is solved through one optimization problem: timing adaptation, location adaptation, and the continuous part trajectory optimization. But adding timing as an optimization problem makes the optimizer way slower, at least twice slower. So this is the price you would pay for adding timing.
Okay, and what kind of solver are you using?
So here we are using an interior point solver, but we have a new version based on ADMM. So Avadesh has developed it recently. He hasn't published it yet. But for the bilinear solvers, we can actually use the kind of optimization using ADMM that handles this very fast. And we can have the centroidal dynamic. There is little guarantee you can give there, but it goes to the desired precision very fast through 1 or 2 or 3 iterations, which is very nice for real time. And he did some MPC based on this, but the paper is not still out, so I cannot give detail yet.
Sounds good. Thanks.
Yeah.